Welcome back, statistics scholars. Today's topic is chi-square. Chi is a Greek letter that looks like an X but is not an X. And if you spelled it out using regular letters, would be spelled C-H-I, kind of like we can spell the Greek letter pi, P-I. C-H-I is chi-square, but the actual symbol is what you see right here, which looks like an X, but in reality is the Greek letter chi. And so we're going to be learning the only type of analysis that we'll do all semester that is called non-parametric, meaning not of the mean. Because what we're going to be dealing with today is null hypothesis significance testing when you only have categorical or qualitative data. So category group-based type of variables. And with category or group-based variables, the average doesn't make sense. And so we're not going to be doing any kind of analysis on the average. No covariances, no correlations, no t-tests, no z-tests, no means, no standard deviations, none of that. Because we only have categorical or qualitative data. And the kind of analysis then we do is called a chi-square. And you should know that the chi-square analysis is actually a really versatile non-parametric analysis that you can use for a wide variety of really advanced procedures. We are going to learn chi-square in two very specific cases. We're going to learn the two most foundational, the most basic, and really the most straightforward uses of the chi-square. There are lots of others. We are going to learn two very basic, straightforward uses of the chi-square, or basically two types of research questions you can ask when you only have categorical, qualitative, or group-based variable information. For example, here, a number of Google results when I blank have kissed her. Now this person, XKCD, Randall Monroe, is classifying the websites based on his Google results. Should have kissed her, shouldn't have kissed him, right? He's classifying the categories into these two groups. This is categorical or qualitative information about the websites. We're going to do the same thing with people. Put people into different groups, into different categories, and then make decisions about them. So, to refresh your memories, when you have a categorical variable, remember it's a variable, so we're going to be asking somebody a question. But then the answer to that question isn't going to be a number. The answer to that question is going to be a word. So we're going to be classifying people by type. We're going to be putting people into different groups or categories. The data is going to be completely discrete, and there's going to be a limited finite number of possible outcomes. So to refresh your memory, things like gender is normally measured categorically, where you each allow people to choose a man or a woman, or even decline to state if you're feeling very inclusive or gender fluid, whatever, people are being put into categories, one or the other. That's typically how it's measured, right? Or let's say your favorite color. The answer to the question isn't going to be a number. What's your favorite color? 3? Does that even make sense? No. Favorite color? My favorite color is red. Or someone else might say, my favorite color is turquoise. Bottom line is people are going to end up in different categories. The turquoise lovers, the red lovers, the purple lovers, the blue lovers, right? Or are you a Ducks fan or a Kings fan? Because in my house, you can't be both. The bottom line is you're making people end up in a particular category. You're not asking how much people like red or how much people like the Kings or the Ducks or how much people have or are on some particular dimension. You're putting people into categories. That is the essence of categorical or qualitative data. And so let's look at an example. I'm opening up a new sporting goods store at Encino, and I'm trying to figure out how to stock college apparel. You may remember this example from very early on in the semester, but in that before, I asked people how much they liked the Brahmas. But now I'm changing my question. I'm changing my variable to give me qualitative or categorical data. And so now I'm asking people in Encino, do people prefer the Brahmas, the Pierce College Brahmas, or do people prefer the Valley College Monarchs? and I'm making people choose. You must choose one or the other. The variable here is, who's your favorite community college mascot? Brahmas or Monarchs? That's the variable. And there's two different outcomes that I'm allowing people to choose from. I'm allowing them to choose between the Brahmas and the Monarchs. And I'm saying you have to pick. You have to pick. And so here is what my data is going to look like. I'm going to grab 50 random people from Encino, and I'm going to tell them to pick a side. You have a choice. Who do you prefer? Do you prefer the Pierce College Brahmas, or do you prefer the Valley College Monarchs? And the first person tells me Brahma, the second person tells me the Brahmas, the third person tells me the Monarchs. Notice how the answer to the question is a word. And so you know that this is a categorical or qualitative variable. Now, in the world of measurements, we'd actually give people numbers. Remember, this would be then nominal measurement. But the numbers are just going to be placeholders. I could then just decide that I'm going to give everyone who chose the Brahmas a 1, and I'm going to give everyone who chose the Monarchs a 0. But the numbers don't mean anything in terms of amount. They're just placeholders. And when I use 1s and 0s, this is actually called dummy coding. And the reason why I have to do this is because I have to keep track numerically of people's answers in most statistical software packages. The common one in psychology and the other behavioral sciences is SPSS, but there are others. There's PSPB, there's a free one called R, there is other ones called SAS, other ones called STATA, there's HLM, there's EQS, there's all of these really cool, sophisticated computer programs that can do all of the stats that we learned all semester for us. They can do the math for us and give us our results. And in these programs, they don't allow you to put words if you want to run an analysis. They make you code your variables. So even though this is a categorical or qualitative variable, I'm going to then nominally code this with the Brahmas as 1s and the Monarchs as 0s. And a 0-1 binary scale is called a dummy code. And in this way, we can communicate with the computer program about the words. But never forget, this is still categorical qualitative data. The 1s and 0s are just nominal. They're just standing in for what we know the real answers are, which are words. And so comes the return of the frequency table. And you'll remember that we use the frequency table to deal with quantitative data sometimes as well. As long as the quantitative data was discrete, and as long as it had a narrow range, we could use a frequency table. But frequency tables are even more useful for categorical or qualitative data because they allow you to keep track of frequencies. And much like the averages were our descriptive statistic of interest in the z-test, the t-test, the f-test, and even in the correlation, just like the average was the useful descriptive statistic, now we're going to be keeping track of frequencies. Averages don't make sense anymore. The average number of people who fall into the Monarch category, I'm going to calculate the average of Monarchs and Brahmas, the average of the 0s and 1s. That doesn't make any sense. So now, instead of keeping track of averages, I'm going to keep track of frequencies. How frequently did the Monarch category turn up? How frequently did the Brahma category turn up? And this becomes our new data that we're interested in. Not going to be calculating averages, not going to be calculating standard deviations. Rather, we're going to be keeping track of frequencies. How many people ended up in the Monarch camp? That is the frequency for the Monarchs. And in this case, I see that 16 people ended up in the Monarch camp. 16 people chose the Monarchs. So that's the frequency of this category. 34 people chose the Brahmas. So there are 34 people in the Brahma camp. That is the frequency of this category. And then if you combine them, that would be then the total sample size. I had 50 total people, and this is how they are distributed, how those 50 people are distributed among the various categories. Now, you don't only have to have 2 categories. When you do a chi-square analysis, you can have as many categories as you wish. 3 categories, 4, 5, however many you have. Because let's say I decided to add another community college in here, or I started to expand my horizons and allow, Northridge to be in here, or UCLA, or whomever. I would then have multiple categories on this particular variable. But for now, we're going to keep it simple. We're going to keep it to 2 categories, where I now look at this frequency table, and I can see that 34 people chose the Brahmas and 16 people chose the monarchs. This is my descriptive data that I'm then going to analyze. It replaces the average. We're dealing with frequency data now and not averages. Here is a relative frequency table. Again, remember, this is just the proportion. 16 people chose the monarchs. That would be 32%, or a proportion of 0.32. 34 people chose the Brahmas. That's 68%, or a proportion of 0.68. Total of 50 people, which then would be a proportion of 1, because 1 is all of it and 0 would be none of it in the world of proportions. We might also want to visually summarize truly qualitative data. And we're going to then do what's called a bar graph. A bar graph is really similar to a histogram, except instead of having the scores along the x-axis, we have our various categories. So here's a different example. Let's say I'm working for a local business group, and they want to know what kind of bars and eating establishments around the college people like, right? And so I decide to grab 100 students from around Pierce College, and I say, here are 5 choices. Tell me which one of these you prefer. And so all 100 of my students are having to choose between one of these various restaurants or pubs. Dirty Bull Tavern, Pickwick Pub, Crazy Harry's Bar, The Rack, or The Rabbit Hole. All actual eating establishments I know because I looked them up on my Yelp app. I've only actually ever been to 2 of these places. But the other ones exist, at least according to Yelp, and I'm making up this data, right? I'm just using it as an example. But let's just say 35 students chose the Dirty Bull Tavern, 15 students chose the Pickwick Pub, 6 students chose Crazy Harry's Bar, 11 students chose The Rack, and 33 chose The Rabbit Hole. It's qualitative or categorical data because I'm putting people into categories. 35 represents frequency data. It represents how frequently somebody chose the categorical outcome of Dirty Bull's Tavern. 11 for The Rack represents 11 people that chose The Rack. I'm putting people into buckets. I'm putting people into groups. I'm putting people into categories. And here is a bar graph. It's sort of like a categorical histogram, right? And where you put, instead of scores at the bottom, you put all the categories at the bottom. Dirty Bull, Rabbit Hole, Pickwick, Rack, and Crazy Harry's. And then you put how frequently a person ended up in a particular category along the y-axis. And you keep the bars separate. You don't smush the bars together like you did in a histogram, because these categories are completely discrete. They're completely separate from one another. They don't run together like a dimension-based variables outcomes would. Right? When we were dealing with more versus less, the bars touched because there was sort of theoretical quantitative space in between all of the numbers. Now, there's no being in between Dirty Bull and the Rabbit Hole. There's no being in between the Rabbit Hole and Pickwick Pub. And so we keep the bars separate. But the height of the bar still represents the frequency, right? Where we can see that the Dirty Bull is much higher, more people chose it, than anyone chose Crazy Harry's Bar, right? It's just a categorical histogram called a bar graph, where again, how frequently a category occurred goes on the y-axis, and the actual category names go along the x-axis, where now we keep the bars separate. So what does this all have to do with null hypothesis significance testing, or calculating an inferential statistic? To remind you, we've already learned to calculate several inferential statistics. We learned how to calculate z-tests, one sample t-tests, independent samples t-tests, paired samples t-tests, ANOVAs, or the F statistic, and we've learned how to do a t-test for the correlation. Now, we're dealing with only categorical data. And because we're not dealing with anything having to do with the average, where all of the other analyses were parametric, dealt with the average, we're now going to do a non-parametric inferential test statistic. But what we're going to be examining now, instead of averages, are frequency data. How frequently did somebody end up in a particular category? And we're going to learn about 2 research questions, 2 only, that you can ask and answer using a chi-square approach with only categorical data. We're still going, but a lot of what we've done is going to be exactly the same. We're going to collect data from our people, frequency counts. We're going to collect frequency information for a sample. We're going to be making a decision about a population where we create a null and alternative hypothesis. We're going to test the null hypothesis by assuming that it's true. We're going to then look up a critical value on a null hypothesis sampling distribution. We're going to then calculate a chi-square test statistic, an obtained observed test statistic. Then we're going to compare our statistic to the critical value. And if what we calculate is bigger than the critical value, reject the null hypothesis. And then we can know whether or not our p is greater or less than alpha. If what we calculate is bigger than the critical value, reject the null, p will be smaller than alpha. If what we calculate is not bigger than the critical value, we will fail to reject the null, retain the null, and our p will be greater than alpha. Now, you could use an online calculator to look up the p-value as a part of our lecture today, but that's not something you're going to be able to do on the exam. And so the way we know about p is by looking at the critical value and the test statistic. If what we calculate is bigger than the critical value, that is how we know p is small. If what we calculate is not bigger than the critical value, that's how we know p is big. So all of that is exactly the same. It's the same kind of procedure that we did for every other kind of analysis. It's just the type of question we're going to ask and answer now is very different because we're only going to be dealing with categorical information. So here are the kinds of things that you can ask and answer with a chi-square test statistic. You can ask this question: does the category seem to matter at all? In this group of people, is there a preference for one category or another? Where we have some research or alternative hypothesis that says it does matter, where we say people have a preference. One of these categories is going to have a whole lot more people in it than the other category. Think about like Coke or Pepsi. Do people have a preference for Coke or Pepsi, where you're making people choose? Well, the research alternative hypothesis, the cool thing would be, yes, people definitely have a preference. I definitely see a preference here. One of these categories, Coke, I would think, or maybe Pepsi, who knows, but one of them is going to have a whole lot more people in it in the population than the other category does. But then you create a model, a frequency model, where you say the category doesn't matter. And that is then called the null hypothesis. You essentially create yourself a frequency world, a model where the frequencies are exactly the same between the different categories. And so using the Coke and Pepsi example, I would then say in the null hypothesis that the exact same number of people prefer Coke and Pepsi, that the category doesn't seem to matter here, that the frequencies are identical between these categories were I to look in the population. So then you test the null hypothesis model. And it's called a model because of how we test it. We look at, and I'll show you that in a minute. This type of research question is called a chi-square, there's that Greek letter chi again, chi-square goodness of fit test. Because what you do is you create a world where the frequencies are exactly the same among all of your categories. And then you test to see how good that model fits. It's poor grammar. It should be how well that model fits, but it's still called the chi-square goodness of fit test. So that I'm going to go ahead and use the poor grammar and say, we're going to check to see how good a null model fits. Basically, the null hypothesis says that the distribution of people among all of your categories is going to be exactly the same. And so if we go back to our Brahmas and monarchs example, there were 50 people. Well, the null hypothesis would say the distribution should be exactly 50-50. 25 people should like the monarchs, 25 people should like the Brahmas. That is our null model. And then the alternative would say, well, the distribution of people among the categories is not going to be equal. And if we can reject the null, then that leaves us with our alternative. And again, we're trying to make decisions about populations based on our samples. And so let's take a look at our data again. So the research question before was, I'm opening up a new sporting goods store in Encino. I'm going to stock college apparel. And I'm curious if in Encino people prefer the Brahmas or the Monarchs. The null hypothesis would say there is no effect of the category. Giving people a choice between the Brahmas and the Monarchs doesn't really seem to matter because people don't seem to have a preference. The exact same number of people in Encino are going to end up in the Brahma category or the Monarch category were I to look in the population. The research or alternative hypothesis is that the category does matter, that people in Encino do have a preference. And so were I to look in the population, I would see an uneven distribution of people into these two categories. More people are going to be in one category versus the other. And so then let's look at our actual data with a frequency distribution. And what I can see here is there certainly seems like there's a preference, right? More people in my 50-person sample are choosing the Brahmas over the Monarchs. But this could be sampling error, right? These 50 people aren't all the people in Encino. A whole lot more people live in Encino than just 50 people, right? And so this could just be sampling error, which is why I have to do a null hypothesis significance test, where I create competing hypotheses. We have to figure out how unlikely a sample with this distribution, 16 to 34, would be if in the population, the real distribution is 50 to 50, right? How likely is a 68% to 32% split if in the real population, the real split is 50-50? If it's super unlikely that I would have seen a 32% to 68% split in my sample, well, then I'm going to reject the null hypothesis, that the idea that it's really 50-50. So it's very similar to all the analysis we've done before, except instead of looking at averages, we're looking at frequencies among categories. And so here is then how I wrap my head around an inferential test statistic. Here is how I'm going to calculate my inferential test statistic. I'm going to create an expected values table based on the null hypothesis. So you might even call this the null table. Now, most of the time in inferential test in chi-square land, we don't call it the null table. It's called the expected table because it's what we would expect to see if the null is true. But you can think of it as the null table because if the null is true, this is the kind of frequency information our sample should have generated. This is our observed table. You might think of it as your research question or alternative table. Now again, most of the time in inferential testing chi-square land, we simply call it the observed table because it's our actual data. But you can think of it as like the competing alternative hypothesis. We see this kind of frequency distribution. This is like our sample data, and we're comparing it to a null hypothesis model, what we would expect to see if the null is true. This is our observed table, and we're going to compare that to our expected values table. Expected according to what? According to the null hypothesis. And so then, this is then how we calculate a chi-square test statistic, where now we're going to have some degrees of freedom, but more on that in a minute. The degrees of freedom are how we're going to look up a critical value, but more on that in a little bit. The chi-square test statistic is calculated by taking the observed frequencies in a particular category, subtracting the expected value frequencies in a particular category, squaring it, which is where it gets its term chi-square. Do that for each and every single category, then divide each of those by the expected value, and then once you've done that for all of your categories, you start at the first category and at the last category C, and then you're done. So you add them all up at the end. This is how we're going to make our decision about our population. This is how we're going to be able to determine whether or not to reject the null hypothesis, to figure out how probable our sample data is if the null is true. And if what we get is really big, really extreme, then we can reject the null hypothesis, because that is it's the same sort of approach. Figure out how likely your data is if the null is true. If the probability of your sample data, if the null is true, is really small, then you reject the null hypothesis. And that allows us to make a decision about the population. Is there an even split between Brahma fans and Monarch fans in Encino? So that is what allows us to make this decision. And we'll work through this example to sort of allow you to wrap your head around what we're doing. We're just asking this question. We're not asking, are the averages the same or equal? Now we're asking, are the frequencies among our categories the same or equal? Where the alternative research hypothesis says the world is interesting. The distribution is unequal. The null hypothesis says the world is boring. The distribution among the categories is exactly the same frequency among the categories. And so here is me calculating this chi-square test statistic. So let me give you the equation at the top here, and let's work through what's happening from the previous, how we're calculating this chi-square. So going back to this data, you notice I have my expected value table and my observed table, right? I've got both. And so here is the chi-square test statistic. This is the chi-square. There'll be some degrees of freedoms, more of that in a minute. It's how we'll look up our critical value. And here's the equation on how to calculate the chi-square. So here is me doing that. My observed value for the monarchs was 16. 16 people chose the monarchs. According to the null, 25 people should have chosen them, right? There should have been an even split. So I subtract to get -9. 34 people chose the Brahmas. According to the null, 25 people should have done that. So I get a +9. I've now done the observed minus the expected frequencies for each category. I'm now going to square those values. -9 squared is 81. 9 squared is 81, right? Now I'm going to divide these squares by 25 because I divide by the expected values. 81 minus 25 is 3.24. 81 minus 25 is 3.24. Add up those quotients. 3.24 plus 3.24 is 6.48. So my chi-square test statistic is 6.48. So now what are we going to do with that? We need to compare it to a critical value. All right, so we're going to take this 6.48, which is our inferential test statistic, and we're going to need to compare that to, that's right, a critical value. Because what is this 6.48 again? Well, this is our inferential test statistic where we first assume that the null hypothesis is true, where we assume that there's no preference for Brahmas versus monarchs in Encino, that the distributions are exactly the same, between the categories are exactly the same. And just like with the Z and T statistics and F statistics, this is our inferential test statistic that we compare to a critical value. If what we calculate is bigger than the critical value, reject the null hypothesis. If what we calculated is not bigger than the critical value, fail to reject. Now, I haven't taught you how to look up the critical value yet, but I promise you I will. It'll be a table in the back of your book based on some degrees of freedom. We could also use with an online calculator we could use this 6.48 to look up the exact p-value, but again, that's not something you're going to be able to do on the exam. But we'll know about our p-value. If we reject the null, then p is small. If we fail to reject the null, p is big. If our chi-square test statistic that we calculate is really big, that means it's very improbable. Its p-value will be small. If our chi-square test statistic is really small, that means it's not very extreme. It's very probable, and its p-value will be big. And just like with every other inferential test that we've done, there is a sampling distribution for chi-squares. And much like with the F test, in the chi-square test, the sampling distributions are based on your degrees of freedom, where the shape is going to change depending on your degrees of freedom. and is very skewed. So we no longer even have remotely normal sampling distributions, just like with the F-test, where our sampling distribution wasn't normal. In a chi-square test, our sampling distribution isn't normal either. That means we're going to have to look up our critical values. We're going to have to know our degrees of freedom, and then we're going to have to look up a critical value based on our degrees of freedom. For example, the distribution here in black is based on 1 degree of freedom. The distribution here in blue is based on 2 degrees of freedom. The distribution here in green is based on 3. Red is based on 4 degrees of freedom. And the pink one is based on 5 degrees of freedom. And in a chi-square test, your degrees of freedom is based on the number of categories you have, not the number of people. And specifically, in a chi-square goodness of fit test, it's going to be the number of groups that you have minus 1. That is going to be your degrees of freedom in a chi-square goodness of fit test. So in our example of Brahmas versus monarchs, because there are 2 groups, our degrees of freedom equals 1. And so we would be using a sampling distribution that looks like this black one to then look up our critical value. So then we would choose an alpha of 0.05, 5% of the graph, whoops, 5% of the black graph, and then find the critical value that cuts off 5%, or 0.05, because that's our alpha, of the graph that is outlined in black there, that I've now shaded in the alpha area with yellow. I did it sloppily. Apparently, I can't color in the lines. Back to kindergarten for me. But every then chi-square with a different number of categories, let's say I had 3 schools, then it would have been the blue distribution. If I'd had 4 schools, it would have been the green distribution, and on and on and on. And so our degrees of freedom in a chi-square goodness of fit test is going to be the number of groups you have minus 1. And so these degrees of freedom then are how you're going to look up your critical value. And the table in the back of your book that allows you to look up critical chi-squares, right? Chi-square, which looks like this, Greek letter chi-square, or you can actually write it out, C-H-I, chi-square, is here. We had only 1 degree of freedom. We're going to choose an alpha of 0.05. That's our type 1 error rate. That is the percentage of type 1 errors we're willing to accept, even if the null is true. That's our alpha, the likelihood of a type 1 error. That is also sometimes called the significance level. And here I can see that my critical value then for an alpha of 0.05 with 1 degree of freedom is 3.841. That is our critical chi-square. If we flip back here to our actual test statistic, we got a 6.48. That means we are going to reject the null hypothesis because 6.48 is bigger than 3.84. Because our calculated chi-square is bigger than the critical value, we're going to reject the null hypothesis. We're going to say that in Encino, people seem to prefer the Brahmas more than they prefer the monarchs. More people prefer the Brahmas over the monarchs. We're going to reject the null hypothesis, and that will mean that P is small. Here, we compared the goodness of fit. We compared the null hypothesis model to the observed alternative model. We calculated our test statistic to determine, we calculated our test statistic of 6.48, compared that to 3.84, and so rejected the null hypothesis. And so then what we did is we simply compared what we observed to what we expected, by subtracting, and I call each of my categories a cell, kind of like we did in ANOVA. Cell 1, cell 2, category 1, category 2. Then I squared them, then I divided, and then I added to get 6.48. I compared that to my critical value of 3.84, and I rejected the null hypothesis. And here then is the process. You choose an alpha level, It's called your significance level. It's your type 1 error rate. It's the number of type 1 errors, the proportion of type 1 errors you're willing to accept even if the null is true. That is your area of rejection also. All of those are different ways of describing the same thing. We have an alpha of 0.05. You get to choose your alpha. We have 1 degree of freedom. Why? Because we take G minus 1, where G is the number of categories. 2 minus 1 is 1. Then we're going to look up a critical chi-square. We just did that. We needed to know our degrees of freedom and that critical alpha that we got to choose. In this case, 1 and 0.05. Our critical value that we just looked up was 3.84. Our calculated test statistic, our observed obtained test statistic that we calculated was 6.48. Do we reject the null? Yes, we do. Would our PV less than 0.05? It certainly will be. And on the exam, you could definitely say that. P is going to be less than alpha. Now, you could use an online calculator to look up the actual p-value. And so I went ahead and did that. And p is equal to 0.0109. And what do you know? It's less than alpha. But you can know that p is less than alpha just based on the fact that you calculated an observed obtained test statistic bigger than the critical value. Just like we did for z-tests, just like we did for t-tests, just like we did for f-tests. It's all the same process. That means that there is a 1% chance of seeing data like ours that the null is true. That's really small, so we reject the null hypothesis. But in reality, we can know that just based on this statistic here. 6.48 is very extreme. So extreme that it's going to fall in the area of rejection on the chi-square sampling distribution. It's bigger than the critical value of 3.841. So we reject the null hypothesis, p is small. And if we look at that on a sampling distribution, here's where it would be. Here is that chi-square test statistic on a sampling distribution of chi-squares with 1 degree of freedom. You can see this is the alpha area here, 5%. Here is that critical value of 3.84. 6.48 is in the area of rejection. It's falling well beyond the area of rejection, right? It's everything in here is alpha. 6.48 falls in the area of rejection. Reject the null hypothesis. P is going to be small. So what does that mean in terms of our research question? If we reject the null hypothesis, what does that mean in terms of our original question in everyday language? Well, in sort of technical language, it means the frequencies are not evenly distributed among the categories. In everyday language, that means people in Encino prefer the Brahmas over the Monarchs because more people chose the Brahmas over the Monarchs, and the split was uneven enough that we could reject the null hypothesis. What we expected to see looked too different from what we actually observed. And that is the chi-square goodness of fit test. And you can do that test with any number of categories where you ask the question, are the number of people evenly distributed among all these categories or not? That's the idea. So that was the chi-square goodness of fit test. But we're going to learn a second type of analysis, a second type of question that you can ask about only categorical data using a chi-square approach. And that is when you have 2 categorical variables. Because remember, in the chi-square goodness of fit test, we had 1 variable, many groups, right? Possibly. Monarchs versus Brahmas, 1 variable, 2 groups. But I could say, do people have a preference for soda pop? Where I have Coke, Pepsi, Dr. Pepper, 7-Up, Sprite. I could have many groups, and it would still be a chi-square goodness of fit test because I only have 1 question I'm asking people. What's your favorite soda pop? What's your favorite this? What's your favorite that? Right? Chi-square goodness of fit is for when you have 1 question, 1 categorical question. Who knows how many groups that you who knows how many groups you have? A chi-square with 2 categorical variables means you're going to be asking people 2 group-based, category-based questions, 2 category-based questions, or they're going to end up in a particular group based on their answers to 2 questions. And this, what I have here, is called the contingency table. It's called the contingency table because it's what group you're in is contingent fancy word, on your answers to 2 questions. For example, I might do a chi-square to ask this question. Is there a relationship between gender and skirt wearing? That is, I want to know, are these 2 categorical variables completely independent of one another? Or are they related in some way? Does the probability of whether or not someone wears a skirt, is it influenced by their gender? Is there some relationship between these 2 variables? And this is a contingency table where I end up with 4 different categories. Men who say they wear skirts, women who say they wear skirts, men who say they don't wear skirts, and women who say they don't wear skirts. These are the frequency sample data I'm actually going to gather. These are going to be my observed frequencies. Out here in the margins are called the marginal frequencies. 300 people wear skirts, 300 people don't wear skirts, 300 people are women, 300 people are men. So there's a total of 600 people. 5 men who wear skirts, 295 men who wear skirts, thus a total of 300 men. 295 women wear skirts. 5 women don't wear skirts for a total of 300 women. 5 men wear skirts. 295 women wear skirts for a total of 300 people who wear skirts. 295 men don't wear skirts. 5 women don't wear skirts for a total of 300 people who don't wear skirts. These are called the marginal frequencies, where you're only keeping track of one category. These are the columns, and these are the rows. I put gender along the columns, and I put skirt wearing along the rows. And this is everything you need to know about this contingency table that we're going to use to do the inferential test statistic, the chi-square test of independence, where we ask, is gender related to skirt wearing? And once again, we're going to compare what you would expect to see in the null hypothesis and what you actually observe in your data, which you're hoping will support the alternative or research hypothesis. And so once again, we've created a null model of the world where skirt wearing and gender are completely unrelated, that whether or not you're a man or woman doesn't increase or decrease the likelihood of you wearing a skirt or not. And this is what we'd see. Because we have the exact same number of men or women and the exact same number of people wearing skirt and not wearing skirts, because our marginal frequencies are the same in our actual data, because we have the exact same numbers of men and women, 300 and 300, and because we have the exact same number of people who say they wear skirts versus don't wear skirts, we can now create a null hypothesis expected value frequency table fairly easily, where we say, because skirt wearing is equally likely, and because gender is equally likely, well, then there should be 150 men who wear skirts and 150 women who wear skirts. There should be 150 men who don't wear skirts and 150 women who don't wear skirts to make up our marginal frequencies. This is what it should look like if gender and skirt wearing have nothing to do with one another. Here is what it actually looks like in our observed frequencies. And now we're just going to calculate the chi-square test statistic again, where we then take every single category and do our observed minus our expected. But now keep in mind, we really have 4 categories now that are made up by our contingency tables. We have men who wear skirts, men who don't wear skirts, women who wear skirts, women who don't wear skirts. So we're going to have to do this 4 times for our 2x2 contingency table. And so we do just that. So I've kept track and I've done it really slow here for you. I've taken 150 and then I've taken 5 because that's like our first cell. That's our first category. And here's that friendly equation for us. I take what I observe, 5, and I subtract what I would have expected in the null universe, in the null model. And I subtract to get minus 145. Then I do this for the second cell. I take, now I'm looking, the first cell, the one I've labeled in orange, are men who say they wear skirts. I take 150, which is what I should see if gender and skirt wearing have nothing to do with each other, and I compare it to what I actually see, which is only 5. 5 minus 150. There's a pretty big split here. So things in the actual universe are looking real different compared to the null universe. And I do the same thing with women. I do that for the second cell, women who say they wear skirts. 295 women actually say they wear skirts compared to 150 where the null would say there's no relationship between gender and skirt wearing. So I get positive 145. I do the same thing for the men who say they don't wear skirts. 150 in the expected null world, 295 in the actual observed world, and I subtract. Then I do the same thing for the women who say they don't wear skirts. I take 5 minus 150. Now I've made this data up, so it's real clean. We're going to do an example of more real world type of data, but I've made up the data just to give you an example. So I've now subtracted the observed minus the expected, and now I'm going to square it. I'm going to square those positive and negative 145s. Then I'm going to divide all these squares, 21,025, and I'm going to divide by what I'd expect to see in each cell. And that's 150 in each case. This is a really easy example. To get 140.17, and then as a last step, I add them up. I add up all those 140.17s to get 560.68. Now, some people like to round to the nearest whole number, and that's fine. That's not a big deal. You're more than welcome to round to the nearest whole number at this point. But I prefer just to follow APA style, the American Psychological Association style, and always round to 2 places, even when we're dealing with something like fractional people. I just like to do that. So we got 560.68. What do I do with that again? I'm going to compare that to a critical value. So let's pop back to my, I'm going to pop back to my critical value table. But first, I'm going to need my degrees of freedom. So, what would my degrees of freedom be for this kind of test? Well, remember, a chi-square degrees of freedom is not based on sample size. Rather, it's based on the number of categories that you have. But in a chi-square test of independence, we're going to treat each variable separately. And we're essentially going to do the number of groups you have minus 1 for each of your 2 variables, and then we're going to multiply them together. And so I like to talk about rows versus columns. So if we look here, we have 2 rows, wearing skirts, not wearing skirts, and we have 2 columns because the first variable, skirt wearing, had 2 outcomes, and our second variable, gender, had 2 outcomes. So applied to degrees of freedom, I can say the number of rows that we had was 2 minus 1. The number of columns that we had was 2 minus 1. And so then I get a total degrees of freedom of 2 minus 1 times 2 minus 1, or 1 degree of freedom. So once again, I have 1 degree of freedom. And so my critical value is going to be the same as it was before for my previous example, 3.84. So if we compare that to our actual calculated test statistic, well, oh my, 560 is much bigger than 3.84. So I'm going to reject the null hypothesis. I'm going to say that gender and skirt wearing are absolutely related to one another, which is certainly what we see here. Women are ever so much more likely to wear skirts compared to men, right, in our actual data. And we rejected the null hypothesis that there was no relationship between gender and skirt wearing. Now, this is a really easy example. Now, why is this a really easy example? This is a really easy example because our marginal frequencies were the same. I had the exact same number of people wearing skirts and not wearing skirts, 300 and 300. And I had the exact same number of men and women, 300 and 300. And so when I made my expected value table, I could then reasonably assume if being a man or woman was completely independent of skirt wearing, I could have 150 people in each of these inner cells. But what happens if I have data that looks like this? What if, instead of having an even split of men versus women, I actually have men being much more likely? There are just more men in my sample. Let's say I'm looking among engineers. I go into an engineering class, and I'm looking at the relationship between gender and skirt wearing in an engineering class. And here I have just a whole lot more men than women, 400 men to 200 women. And let's say when I look at skirt wearing versus not skirt wearing, I actually see not wearing a skirt as simply way more likely than people wearing skirts. I have 150 women claim they don't wear skirts because maybe women engineers are not likely to wear skirts. Where I have 50 women wearing skirts. Skirt wearing in this engineering class is just a whole lot less likely, period. And being a man in this engineering class is just a whole lot less likely, period. Can I still assume, even if gender and skirt wearing have nothing to do with one another, 150, 150, 150, and 150 for my expected values? And the answer is no. I can't assume that. Because even if gender and skirt wearing are completely independent, even if the exact same probability of men wearing skirts is the same as the probability of women wearing skirts, and the probability of men not wearing skirts is the same as the probability of women not wearing skirts, I cannot assume 150, 150, and 150, and 150. I'm going to now have to calculate my expected values. Because even if gender and skirt wearing have nothing to do with one another, my biggest group should still be men not wearing skirts, because I simply have more men, period, and more not skirt wearing, period, even among the women. And so even if gender and skirt wearing are completely independent, I should still see this as my biggest group. And because I have fewer women, and because I have not very many people wearing skirts, women not wearing skirts should be my smallest group. And so I'm now going to have to, even in that null hypothesis universe where gender and skirt wearing are completely independent. So now I'm going to have to actually calculate my expected frequencies to create my null hypothesis expected value frequency table. And here's how I do it. I'm going to take I'm going to look at my actual data. Here's my actual data. 5 men claim they're wearing skirts. 50 women claim to wear skirts. 395 men claim not to wear skirts, and 150 women claim not to wear skirts, right? My table's a little off here. Let me fix it. All right, that looks better. All right, so I've got 5 men who wear skirts, 50 women who wear skirts in this engineering class. I've got 395 men who don't wear skirts, and I have 150 women who don't wear skirts. And I'm trying to figure out if being a woman or a man is increasing or decreasing the likelihood that someone is going to be wearing a skirt. Is gender related to skirt wearing? Except now, for every single one of these 4 categories, I'm going to have to calculate what I would expect to see if gender and skirt wearing are unrelated, because my marginal frequencies are not the same. Whenever your marginal frequencies are not completely equal, then you're going to have to calculate your expected frequencies instead of just assuming an even split among all the categories. And how you do it is by taking the frequency for the row for that particular cell, multiplying it by the frequencies of the column for that particular cell, and then dividing by the total sample size. And so let me show you how I would do that for this example. So here is I'm now creating my expected value frequency table. I take the marginal frequencies from my actual data. Here are the frequencies for the columns. I have 400 men and 200 women. That is the frequencies for the column variable of gender. Here I have the frequencies for the rows. 55 people who wear skirts, 545 people who say they don't wear skirts. This is the frequencies for the row variable of skirt wearing. Now, to figure out my expected values, I'm essentially figuring out, based on how many total people there are in each of the categories, how many people I would expect to see, even if there's no relationship between gender and skirt wearing. So in cell 1, the orange cell, I'm going to take 55 because that's the number of people wearing skirts who say they wear skirts, independent of gender. Multiply that by 400 because that's the number of men. 400 times 55 divided by the total sample size, that's how many men should be wearing skirts, even if gender and skirt wearing have nothing to do with one another. I do the same thing for my women who wear skirts. I take the total number of people who wear skirts, 55, times the total number of women. I take 200 times 55, and I divide by 600 because that's how many women there should be wearing skirts if gender and skirt wearing have nothing to do with each other. Notice that 55 is small, 200 is small, so this is going to end up with the smallest number because that's what you should see. Less women in the room, less skirt wearing in the room. Even if women and skirt wearing are completely independent, this should be my smallest group. I do the same thing for this pink cell, this pink category here. I take 545 because that's how many people don't wear skirts. I multiply it by the total number of men. Then I divide that by 600. Notice that this is a big number and this is a big number, making this number going to be the biggest number because that's what should be the biggest group, even if gender and skirt wearing are completely independent. The men not wearing skirts should be the biggest number because that's just the base rates of the room. That's what a base rate, and a base rate simply means when you're looking at how often something occurs. Because being a male, or being a man rather, is the higher frequency, and because not skirt wearing is the highest frequency, even if gender and skirt wearing are completely independent, even if being a man does not increase or decrease your likelihood of skirt wearing, this should be the biggest group. And calculating the expected frequency this way ensures that we're creating an expected value null hypothesis table that's accurate. And then I do this for the last category. For my women who don't wear skirts, what I would expect to see if the null was true was 545 times 200 divided by the total sample size. And so voila, this gives me my expected value table. Now, you can round to the nearest whole number. You could round this up to 37. You could round this down to 18. You could round this down to 363. And you can round this up to 182. Because we're dealing with fractional people, many people do in fact round this way. I try to stick to APA style and keep the decimals, but it's up to you. It's by convention, people round, other people by convention don't. It's sort of just what you prefer to do at this point. So, but now I've now calculated my expected frequencies. There should be around 37 men who wear skirts if gender and skirt wearing are completely unrelated. Being a man does not increase or decrease the likelihood of skirt wearing. There should be about 18 women who wear skirts if gender and skirt wearing are completely unrelated, because wearing skirts is not a very high base rate activity. Not very many people are doing it, and there are fewer women, so there should be only 18 women wearing skirts if your gender does not influence the probability of you wearing a skirt. Now we have around 363 men not wearing skirts is what I should see if the null is true. And I should have about 182 women not wearing skirts if the null is true. So now I've got my expected value table. And now I can just compare and contrast. Now again, I've kept the decimals. You can round. It's completely permissible. Just make sure to round appropriately. Now I'm just going to calculate my chi-square exactly as I did before. I take what I actually observe in my data, 5 men wearing skirts, and I subtract what I would expect to see that I unfortunately had to calculate because my marginal frequencies were unequal. So I take 5 minus 36.67, then I'm going to square that. Then I do that for now, and then I divide by what I expect to see. So I'm doing this for the orange cell, men wearing skirts. What I observe minus what I expect, square that, divide by what I'd expect to get 27.35. Then I do that for my second group, women wearing skirts. What I actually observe of 50 women minus what I'd expect to see, 18.33. Square that, divide by what I'd expect to see to get 54.72. Now, of course, in your lab, you're going to have to show each and every single step. I'm just truncating it because this is our second example in the interest of time. You need to show me each and every single step, right? Right. So I do this for my next group, 395 minus 363.33, and then I square it. And then I divide by 363.33 to get 2.76. And for my last group, 150 minus 181.67, square that, divide by 181.67 to get 5.52. Then at the end of the day, I add all of these up to get 90.35. And that is my chi-square test statistic that I'm going to compare to a critical value. And I want you to notice this. There were far fewer men wearing skirts than what the null would expect. being a man was decreasing the likelihood that someone would wear a skirt. Here, there were far more women wearing a skirt than what we would expect to see if the null was true. Here, there were more men not wearing skirts than what I would expect to see if the null was true. And here, there were far fewer women not wearing a skirt than I would expect to see if the null was true. So these values led to this large chi-square. What we expected to see was different than what we actually saw. Being a man was decreasing the likelihood of wearing a skirt, and being a woman was increasing the likelihood of wearing a skirt. That's the bottom line. And you can look at these differences to sort of look to see what's driving the pattern. And so I can then compare this to a critical value. What critical value? Well, I have 1 degree of freedom, right? Because the number of categories, the number of columns I have is 2. The number of rows I have is 2. 2 minus 1 is 1. 1 times 1 is 1. That's how we figure out the degrees of freedom for a chi-square test of independence. You remember that? That's right. And so now I can look up my critical value in that chi-square table right here. I have 1 degree of freedom. My critical value is 3.84. And so then I can, that's right, reject the null hypothesis, because this value is so much larger than the critical value, this calculated, observed, obtained chi-square test statistic. This is our chi-square test statistic with 1 degree of freedom of 90.35 is way bigger than the critical value of 3.84. Reject the null hypothesis. And so we can then confidently say that gender and skirt wearing are not independent. Not independent, where your gender is influencing the likelihood of whether or not you wear a skirt. Being a woman is increasing the likelihood you wear a skirt. Being a man is decreasing the likelihood that you're going to wear a skirt. And so let's do one final example that's even more difficult. Because it's not quite as obvious that these things may or may not be related. Gender and skirt wearing, we kind of know that they're related, right? And so we're going to have to then look at an example that's not quite as intuitive, is what I'd like to do now. Here, I'm going to look to see if party people are party people and party poopers are party poopers. I'm going to ask people 2 questions. So I'm going to have 2 categorical variables. I'm going to ask a group of 600 people whether or not they like karaoke or dislike karaoke. And I'm going to ask these same people whether they like dancing or dislike dancing. So I'm now going to have, this is a 2x2 contingency table, because what category someone ends up in is contingent upon their answers to both questions. So I have 193 people who are my party people. They both like karaoke and like dancing. I have 153 people who are my party poopers. They both dislike karaoke and they dislike dancing. 89 people who like to karaoke but dislike dancing, and 165 people who like to dance but don't like karaoke. And I'm curious if liking karaoke is the likelihood of liking dancing, as well as disliking karaoke increases the probability of disliking dancing. If there's some relationship between these categories, is the likelihood of liking one related to the likelihood of liking the other? And because my marginal frequencies are not the same, I'm going to have to calculate my expected value frequency table. I have more people who like to dance, but more people who dislike karaoke. And so even in a world where the null is true, and these 2 variables are completely unrelated, people who dislike karaoke but like to dance should be my highest category. And just eyeballing it, I can see that that's not true. And because fewer people dislike dancing and fewer people like karaoke, this should be my smallest group. Well, it is my smallest group. So I'm going to have to actually calculate my expected value table. And I do it this way. I'm going to look at my marginal frequencies, and then I'm going to multiply the frequency of the row by the frequency of the column, and then divide by n to get my null hypothesis expected value frequency table. And I do it this way. For my first cell, liking karaoke and liking dancing, even if these two groups are completely independent, these two categorical variables are completely independent, in order to calculate this expected value table, cell value, I take 358, because that's the frequency of the row, times 282, the frequency of the column, divide that by 600, and put that number here. I do the same thing for this disliking karaoke and liking dancing. I take 358 times 318, divide by 600, and put that value here. Then I take 242 times 282, 242 times 282, and divide that by 600 to get this value here. Then I take, for this last one, 318 times 252, and divide by 600 to get this value here. And that gives me my expected value table. Now again, you can round to the nearest whole number. Lots of people do. I like to maintain the decimals, just in the interest of maintaining APA style. It's just a style guide for psychologists. And so these is what I would expect to see if people whether or not you like dancing has nothing probabilistically to do with whether or not you like karaoke, right? And so now I have my null hypothesis expected value frequency table. And I can then compare that to what I actually observed. Now again, I have truncated the math here. I've set up the problem, but not shown you each and every step. I did that for the goodness of fit tests. You will need to show each and every single step to get full credit on your lab assignment, or if you should happen to see a problem like this in your exam. You have to show me each and every single annoying step. But here's what I did. I took 193, because that's what I observed, minus 168. And notice, people who like both is more likely than what I would expect to see if the null was true. There are more party people who like both, than what I would expect to see if the null was true. 193 minus 168.26, square that, divide by 168.26, and then I get 3.64. Then I do the same thing for here. People who like to dance but dislike karaoke. And I notice that I have 189. That's what I would expect to see if there was no relationship. What I actually see is 165. So there are fewer people that only like one. Fewer people that only like to dance but don't like to karaoke. There are fewer people in here than I would see if there was no relationship. Then I do the same thing here. People who like to karaoke but dislike dancing. I see that there's 89 people, so fewer people who only like one versus the other than what I would expect to see if the null were true. And finally, here are my party poopers. 153 is what I actually observed, so more people that dislike both compared to what I'd expect to see if the null were true. So once I do all this math in here, subtract, square, and divide, subtract, then square, then divide, subtract, then square, then divide, I can add all these together to get my chi-square test statistic. And I would compare that to a critical value. How many degrees of freedom do I have? Well, the rows minus 1, 2 minus 1 is 1. The columns minus 1, 2 minus 1 is 1. 1 times 1 is 1. So I have 1 degree of freedom. Well, with 1 degree of freedom, my critical value is 3.84. My chi-square test statistic is 16.87. So I'm going to reject the null hypothesis. It looks like if you like karaoke, you're more likely to like dancing. And if you dislike karaoke, you're more likely to dislike dancing. There are, in fact, more likely to be party people and party poopers than people who only like one. And I can know this because my calculated chi-square is bigger than my critical value. And then I'm going to know then that my p is less than alpha. I use a critical value of 0.05. A critical alpha of 0.05. I get to pick this. It's my type 1 error rate. I have 1 degree of freedom because I had 2 rows, minus 1, 2 columns, minus 1, 2 outcomes. I had liking karaoke, not liking karaoke, liking dancing, not liking dancing. So 1 times 1 is 1. So I have 1 degree of freedom and an alpha of 0.05. I looked up my critical value of 3.84. My calculated observed test statistic was 16.87, so I reject that null hypothesis. And I know for sure that our p is going to be less than alpha, that whether you like dancing and whether you like karaoke are related. They are related to one another. They are not independent. Not independent. And when I actually use an online calculator, which you cannot do on your exam, and you don't need to do on your lab, but if I did look it up, I could see that my P was super small. The probability of seeing this test statistic, if the null was true, is very small. Our actual observed data is super improbable compared to the null hypothesis expected value table. P is small, we reject the null. Our calculated observed chi-square statistic was big, so we knew for sure that our P had to be smaller than alpha. When I went ahead and looked it up online, I see that it actually is. And that is chi-square, 2 different kinds of chi-square. And our last topic for this semester is actually going to be not calculating any more statistics. Chi-square is actually our very last analysis that we're going to learn. And to keep track, we've learned z-tests, one sample t-tests, independent samples t-tests, paired samples t-tests, ANOVAs or F statistics, and then we learned how to calculate t-tests for correlations, and now we've learned how to calculate chi-square test statistics when you have one categorical variable, goodness of fit test, and for when you have 2 categorical variables, chi-square test of independence. The last sort of step in our arsenal of knowledge is learning when to do what test. Because in real world research situations, there's not going to be anybody here to tell you. So our very last lecture that we're going to have for next time is how to know what test to do. Because chi-square is actually our last test. We've learned to do them all! Hooray! So I will see you next time where we go over how to know what test to do. See you next time.